not that significantly long. There are a lot of new concepts that I want to develop first regarding electric circuits, and so that'll take a little bit of time. And so what I want to begin with is kind of where we left off with voltage in our last lecture, and we'll still have a little more to speak about in terms of voltage from chapter 24 on Tuesday. But with respect to an electric circuit, we can combine together the principles of electric potential with actual motion of electrons. And so essentially, this is the cause, which is a difference in voltage. Between 2 points. It's always a difference in voltage. For example, we could have instead of having this kind of symbolic representation for a battery, in which the longer side is the positive and the shorter side is the negative, we could draw a real live battery, represented a little more physically. And we could say, let's for example say that this is a 12-volt battery, which means that if I took the voltmeter and I put the positive end on this side and the negative end on that side, it would measure 12. And so we did that last week. Now this is just potential to do work. Remember that to do work, we have to move a charge through that difference in potential, Q delta V. So work is total charge moved through a change in voltage, delta V. Okay. And so we're interested in that, of course, with electric circuits, because electric circuits can do work. And that work is important in a whole wide range of applications. Most, probably, I don't know, 80% of our technology is based on this kind of work that is done by electricity. And the nerves and the muscles and our brain cells also work off of that same kind of energy. So this is a very widely applicable topic. And so this would be the work that we do when we move a charge through a certain difference in voltage. So nothing's happened here yet. And so we can kind of think of that as being kind of like, and I'll use some water analogies here. This is like water pressure. Not the same thing, of course. But it's kind of like it. There are a lot of analogies to water that I think are useful, because it's hard to visualize 6.3 million electrons moving through a cross-sectional area in 1 second. But you can think in terms of, say, a water faucet here. Now, if this were a drippy water faucet, then I would be worried about leaving the tissues under there, because I know that the water would flow onto them. But as long as there's no path for the water to flow, this is just a potential to make the tissues wet. Now, if I want to allow for a path for the water to flow, I open that up, and then the pressure can go from high pressure to low pressure. And the sum of the forces doesn't balance out. Similarly here, I could take a wire, and being a conductor, the wire would allow for the flow of electrons between positive and negative. And the electrons would go this way, even though positive conventional current is considered to be in the opposite direction. And I'll explain why we use this concept of conventional current, even though it's in the opposite direction from electron flow, a little later on. So we can imagine then that when we open up this valve, that allows for a flow of water. But the flow of water is also influenced by, let's say we have this thing going through a pipe, and it was really constricted pipe, then there'd be more resistance to water flow, so the water flow would be smaller. And similarly here, we can think of this resistance as being an impediment to electron flow. Okay, and so if we were to look at an electron as it passes from one side to the other, it might follow some kind of a obscure path like this, in which the electron would be moving in the opposite direction from the electric field. And so what the battery does here is it produces a local electric field within the wire that is relatively constant. And then the charges, that's different from this one here, but I'm trying to set it so it's consistent with the way I do this battery. So in this case then, the electrons would be moving in the opposite direction from the direction of the applied electric field. So we can, of course, understand that by just saying, well, what caused that electric field? Well, it's got to be positive on this side and negative on that side, because electric field lines lead positive and terminate on negative. So if I just put my little positive and negative in here, I can see that negative will repel negative and negative will attract positive. And so clearly then the electron flow is in the opposite direction from the applied electric field, which we could also write as F equals QE, where in this case Q is negative, making the force anti-parallel to the electric field. And so the electrons then move through, but because they're knocked back almost as often as they move forward, they have a very slow terminal velocity. So the electrons then don't speed up much, but they reach a terminal velocity. And we call that terminal velocity the drift velocity. Which is Vd. And so that's just our average velocity of electron flow through the wire. Now, if you had electrons accelerated in a vacuum tube, you could get them going a third the speed of light on their way to a phosphorescent screen in just a very short distance. You can get them going a third the speed of light. So the electrons are very light, very easy to accelerate, but because they're so easy to accelerate, they're easy to knock back too when they hit a bunch of obstacles that are in the way. So the resistance then is a measure of how many obstacles there are in the way of the electron as it tries to beat its way through the wire. And normally when we say that we do work, if it's in a vacuum, we could say that work done is 1/2 mv squared. You know, it would just be the change in kinetic energy. But the kinetic energy will stop increasing when we reach the terminal velocity. So this is just like what would happen if you jumped out of an airplane. You'd be traveling about the same speed when you hit the ground if you jump from 1,000 feet or from 10,000 feet. Because eventually, as you fall faster and faster, the resistance force would be proportional to the velocity that you're moving, because you're pushing more air molecules out of the way as you fall, until finally those forces balance, and at that point you reach terminal velocity, maybe about 180 miles an hour or so, depending on how open you were, or whether you were in a swan dive, or how resistive your streamlined trajectory was. And so this is analogous to that, but for the case of electrons, the drift velocity in a wire with a typical current might be in the order of a few centimeters per second. Which means that as a current is flowing through this wire, we could essentially walk alongside of the average velocity of the electrons as they move through the wire. Now, because the electrons, basically then what the resistance does then is it controls the flow. And the goal is to keep the drift velocity down. Because if the drift velocity gets going too fast, or if it starts to speed up, there's not enough things in the way to slow it down, then it'll hit those atoms so hard that it'll give a huge amount of its energy to those atoms. Those atoms will start to vibrate very rapidly. And if this were just a small piece of connecting wire with very low resistance, the current would get very high. And so what that would do then with a low resistance is it would make a very large current, and then the current is the flow of electrons moving with a certain drift velocity. And so we could think of the current as being related directly to the drift velocity. And so the faster these electrons are moving, the harder they're going to hit those atoms, and so it's just going to melt this thing or burn it up. And so you use the resistance then to keep the electron flow under control so that you can do useful work, but controlled work. Question?
Kind of chemically, what is happening when electrons are moving? Are like the valence electrons in atoms being traded and moving along, or like are they just completely free floating through the metal?
In a conductor, you have a smaller pull on the outermost electrons than in an insulator. And so those electrons are easily knocked loose. And if they were in isolation, they would go up to some higher energy state or be completely ionized from the material. But when you add a bunch of them together, what you end up getting is what's called a conduction band, which is a range of energies in which the electrons can kind of freely, this kind of leapfrog from atom to atom as they move. But as you add together all these wave functions for all of the different atoms, you end up getting something that has different properties from what you have with a single atom. So instead of just completely ionizing it, it moves it into a certain range of energies in which the electrons can freely conduct through the material.
Gotcha. Thank you.
Yeah, and so the whole study of that is pretty extensive, and that's called solid-state physics. But that it gets into things like the Fermi energy and what it takes to get electrons moving through. And then you also get into quantum mechanics because you end up with energy barriers that that electrons couldn't overcome classically, but they can tunnel through them quantum mechanically quite easily. And so that has a lot to do with resistance, is the probability for electron tunneling. And so it gets, I mean, this very simplified explanation is, when you start looking at it more carefully, you realize that it's really way more complicated than that.
Okay.
And so, if, let's say that we're designing a water slide for kids, and here's the water down there. And so then the kids go down, we go, well, we haven't really tested this out yet, so let's, but we've already built the water slide. And so this kid, unfortunately, gets going like 100 miles an hour and then kind of crashes and burns in the water. The lifeguard comes in, but they're able to revive him. So I go, well, we've got to make some design changes. And so they go, I know what we could do. We'll just put sandpaper at various spots along the path. And so that'll slow it down. And so as the kids start to go then, they hit these, this one starts to slow down, and then the next one gets anxious and wants to go. And so they all then are slowed down to essentially terminal velocity. And so where's that energy going then? Instead of going into increasing the kinetic energy. Heat and pain, right? as they hit the abrasive surfaces there. But that would be a way then of keeping the velocity of the kids on the water slide under control, so that we don't get a disaster down here. And that disaster would analogously be to, say, a big fire when the wire burns up and your electrical device catches on fire. Okay, and so instead of that energy then going into speeding up the electrons, it goes into doing some kind of work. And so that work could be heating up a heater filament. Or it could be, if you were, say, talking about a light filament, you could have an electron that could move along. It could slam into this electron, and the kinetic energy from this electron then could give this electron just enough energy to go up to a higher energy state. In that higher energy state, it would be unstable, would decay back down to the ground state, and would produce a photon of light. And so that's what we're seeing then here, is that electric current being turned into light. Okay? And you can turn it into mechanical energy by means of an electric motor. And we'll talk more about how that works later. And so we've got zillions of different ways then that we can do work by allowing a flow of electrons through a wire. But we don't want the current to get too high, and so we use the resistance to control the flow. If the resistance were 0, then the current would go to infinity. But way before that happened, the metal would melt or the thing would catch on fire. So if we go back to this picture then, instead of seeing this as being just like a lampshade wire here, and this being a source of voltage, we could draw this kind of a more schematic representation in which the longer side of the two parallel lines is the positive side of a battery, and the shorter side is the negative or ground side of the battery. Then we would draw conventional current as going in this direction, but electron flow would be in the opposite direction. So why define it that way? Why define it in the opposite direction from electron flow? Well, some people like to blame it on Ben Franklin for guessing wrong on the charge of an electron. But in some engineering classes, we still do speak in terms of electron current. And so it's not the idea of defining the current in the direction of electron flow is not completely forgotten. And in some cases, it may make things a little simpler. But if we define the current in the following way, we can see why it is more convenient to define the current as going from positive to negative. So we can define current as being the total charge crossing a given area in a given time. And so if we just have a regular conductor, and by the way, these conductors are often have insulators around them, what we call the insulation for the wire, so that the electrons don't just flow out in the wrong direction. We want to keep it funneled through the tube, the conducting tube, and not sneaking out, leaking out somewhere else. And that's kind of like the banks of a stream in a way, you know, that keep the water funneled as it goes along its path. And so if we think of the distance that's traveled by the electrons in a given amount of time as being v drift times delta t. This would be the cross-sectional area of the wire. This is just rate times time equals distance. Then we can think about the volume of the wire that is the charge moves through in that amount of time as being delta x times A. So that's just the area of a cylinder, basically the base, pi r squared, if this were a cylinder, times the height. And we can define the current I as being equal to n q electron times v drift times the area. Okay, so n here, this is the number of charges per unit volume in the conductor. So this is different for, say, copper than it would be for iron. This is just the number of available charge carriers. This is the charge on each charge carrier, which is an electron. This we saw before is the average velocity of the electrons. The drift velocity. This is the cross-sectional area. And so we can analyze, at least from a unit perspective here, this would be the number of charges per unit volume, and the volume that we would be talking about in a given amount of time. In a given amount of time, we'd take all the charges in here and we'd empty them out. So they'd go through this area. So all of these charges in this amount of time will move through that area, and so that has a volume then that would be equal to A times delta X. Then you'd have the charge on each electron. So this is the total amount of charge divided by the volume, these two here. So the number of electrons in that volume divided by that volume times the charge on the electron times, and then here we could think of the area times v drift. We could think of that as being delta x over t, like that. Okay, so this is v drift, this is the area, and this is the total. This is the total number of electrons in that volume. But here, delta x times A cancels out, because that's charges per unit volume. So this just gives us the total charge that crosses that area in a given amount of time. Okay, and so that's the reason why this expression works for the current. And of course, we're assuming here that we have a constant cross-sectional area. So this is a simple expression for the current. we see that the current is directly proportional to the velocity. So that we could think of this as being very much like a single charge moving with a certain velocity in terms of the kinetic energy should go like something that would go like I squared, because the drift velocity squared is how the kinetic energy goes. And so we'll see that later when we look at the work that's done. We can write it as I squared R, which would be a good way of thinking in terms of this as being proportional to the velocity squared, which is related to the kinetic energy. But the point that I wanted to bring forth here is that if we take these two and we make the charge negative, but we make the drift velocity negative, then the two negatives cancel out. Okay, so saying then that electrons are traveling this way with a certain drift velocity is completely equivalent to saying that positive charges that have that same amount of charge are moving in the opposite direction. Because if you take the negative and you multiply by negative drift velocity, you get a positive number. And so why have two negatives in there when you can just cancel them out and say, well, this is equivalent to a positive charge carrier moving in the positive direction. And so that's the justification for defining the current this way as going from positive to negative, rather than in the direction of electron flow, which is negative to positive. It just makes the math a little simpler, not to have all those negative signs in there. But we do have to realize that when we do that, that current flow in this direction actually means electron flow in the opposite direction. Minus QE times minus V drift, that's the same thing as plus QE times plus V drift. So mathematically they're identical, and we don't have as many minus signs to worry about if we just define positive conventional current as being from positive to negative. And so once we have that idea under control, then the next thing that we can look at is how do we actually use this equation to solve circuit problems. And so that, of course, is what we're going to be doing today in lab. So let's say that we've got, this could be like a battery again. So this could be the real situation, plus, negative. And then we got some resistor going like this, R. So let's say delta V is 12 volts and R is 10 ohms. Okay, so we already know the units, delta V, is going to be in volts, which is a joule per coulomb. The current is measured in amperes, and that's a coulomb per second. Okay, now how much is a coulomb? Well, we said before, 1 coulomb is equal to 6.3 times 10 to the 18 electrons. So if we have a 1 ampere current, that's equivalent to 6.3 million electrons going across a given area at a given time. Now sometimes they might be getting knocked back, but we're talking about the net flow in a given time. And so on the average then, this would be how many electrons would be flowing across a given area in a given time. And so because it's so many, I think it is kind of useful to use an analogy, something that's easier to picture, maybe like water flowing, something like that. But perhaps the number of water molecules might be comparable to this anyway. So if you really break it down, something that seems like a simpler water analogy may actually be pretty comparable. And the level of complexity, if you actually look at each of the individual atoms. Question?
How did, so cool is
Coulomb?
But I thought it was no cool, the number of electrons.
Yeah, that's cool.
That's a Coulomb.
I thought a coulomb was a charge.
That the charge of 6.3 million electrons.
Got it.
Okay, so in other words, if you took 6.3 times 10 to the 18 and you multiplied it by the charge on an electron, which is 1.36 times 10 to the minus 19, you would get 1. So this is the charge on an electron times the number of electrons equals 1 coulomb. So 1 coulomb is equivalent to this number of electrons worth of charge. Okay, and so the current then would flow. So let's figure out what the current would be in this situation. I then would be delta V over R. And so we have a value here for R, 10 ohms, and for delta V, that's 12 volts. So that would give us 1.2 amperes. Okay, so that would be 1.2 times 6.3 times 10 to the 18th power electrons crossing that given area in a given time. But because a typical electrical device runs off of amperes, we use that unit of measurement rather than using a more elementary unit of charge. You know, we could call the charge on an electron 1, but then the numbers would be huge for everything. So why not, you know, it's like if I had the length of this room in angstroms, which is 10 to the minus 10 meters, the numbers would be so big you wouldn't know how big the room was. But if I say 30 feet, then you know what that means because that unit of measurement is more comparable to the size that you are measuring. And so that's why we use amperes instead of some huge multiple of the elementary charge on an electron. Okay, now once we've established what the current flow is, then we could get the power. Now how do we get that? Well, we can say that work is equal to Q times delta V. And so power is work over time. So Q over time is the current. So if I take the basic definition for work and I divide both sides through by T, what I get is power, P, is equal to current times voltage. And of course, this is an average value. I'm not talking about instantaneous things with calculus here, but it also works in an instantaneous situation as well. So the current times the difference in voltage is the power. So I can figure out the rate at which energy is being delivered to this resistor in this problem. P for this problem then would be 1.2 amps times 12 volts. And so that would be, let me see, 10% of that would be 1.2, 2.4. So that would be 14.4 watts, or 14.4 joules per second. So in 1 second then, the resistor would get power times time, this is joules per second. So in 1 second, the resistor would be getting 14.4 watts worth of energy. And then that energy could be used to power an electrical device or do whatever kind of a function you want it to do. All right, so those are some of the basics. I'll go over some more of the basics on Tuesday, but I'm not going to go over this part of it. So this is your intro lecture on, and Mark's recording it, so we know it's important if Mark's recording it. So what we might be interested in doing then is looking at, because electric circuits involve many different circuit elements and do lots of really clever things, might be interested in some of these basic principles. And so what I'd like to outline for you here is what we call a series circuit. In a series circuit, we have resistors that are one after another. So I'll start with 2 resistors, but then eventually in this lab we'll go to 3. But the basic idea is the same, whether it's 2 or 3. So here we've got our voltage source. Here's resistor R1, second resistor R2. For our purposes here, we'll have R1 be 500 ohms and R2 will be 1,000 ohms in this lab. And our source of voltage will be either 5 or 10 volts. So in other words, we'll do both, a 5-volt source and a 10-volt source. And see, you've done this before. Last week, you adjusted the amplitude on the power supply in order to get 8 volts across the dipole and the line-line configuration. So you already know how to do that. This is your power supply. This is the positive and the negative. But now we're going to want to hook it up to an electric circuit. So this electric circuit involves resistors. Well, what's the value of these resistors? Well, there's 2 ways that we can get the resistor value. One is by using the color code. And so that's not completely obsolete, so we're going to go over that. With the color code, what you'll see is that there's a set of banded colors on the resistor. And so you want to start from the side that has basically the regular colors. You don't want to start from the side that has the gold and the silver. The gold and the silver side is for tolerances, like plus or minus 5%, stuff like that. So start from the other side, and then one way I can measure is to have this meter set up just exactly the same way as we set it up last week to measure voltage. We'll just flip this thing to the ohm setting, which is the Greek letter omega. And then, and you don't want to have anything hooked up to your resistors when you do this. You don't want to have wires hooked up to them. And you definitely don't want it hooked up to the power supply, because then you'll also be measuring the resistance of the power supply if you do what I'm about to do here. What I'll do is I'm just going to come down like this, and I'm going to touch the 2 sides. What the meter does is it sends a small current through here, and by measuring the current with a known voltage, it calculates the resistance. And so the resistance in this, now if you don't have anything on there, it'll say OL, that's overload. That means infinite resistance. And you can also double check that if you touch them together, you should get 0. If you get 0 when you touch them together, that's good because the wires themselves have resistance, but we want to calibrate those out. So normally that shouldn't show up. You shouldn't have any resistance if you just touch these 2 together. But you'd be getting 0 here. And I'm actually getting 0.1. But that's a possible source of error if you're not getting 0. Okay, so what I got, when I measured that was 500. But then I look at the color code, and I'm seeing green, black, brown. Okay, so this is our resistor color code. So this is black, brown, red, orange, yellow, green, blue, violet, gray, white. Okay, and there is a memory device for remembering that, but I don't think that I can say that one anymore. So I'm just going to leave this as it is. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and so the first 2 colors are a number, a 2-digit number. So in this case, the green would be a 5, the black would be a 0, and then the third color is a power of 10. Okay, so the third color here is brown, So that means 50 times 10 to the 1. So the 1 is the exponent of brown here. And so that's 500. So what you can do then in part 1 here is measure the resistance and compare the results to the color-coded values. So that's on the front page. So that's only number 4. And don't worry about that table. You just need 1% difference for each resistor. Okay? So you just have 3 calculations between the color-coded and the value that you get off of the digital meter. And we won't use the analog meter because we don't want to make this lab too involved yet. We'll get to some more sophisticated things next week after I've had more of an opportunity to introduce circuits, which I'll be doing most of next week. Okay, so you can get those color-coded values, measure the resistance, and then you'll have them. Then we'll have this 2-resistor circuit. It's in series like this. So this is our delta V. These are the resistances, and here's the current. Okay, so a property of these series circuits is that the voltage differences across each of the resistors, if I take and I measure the voltage across R1, I get V1. If I measure the voltage across resistor 2, I'll get V2. So this just goes in on the hot and the ground side. So that's really easy to do. You've already measured voltages last week, so you're just measuring across each resistor. Then you can compare that to the total voltage, which you can get by going over both resistors by just going from one side of the battery to the other, or from going from one side of the resistor to the other. And so to get that working here, you'll need a connecting wire that comes in to one of your resistors like this, and then you'll need a second connecting wire, and just try to picture what's going on here. The current is flowing this way, through this resistor, then through that resistor, and since we're only doing 2 at first, then we'll just bring this back. We'll just bring this back, oh, here we go, this here. We'll just bring this back to ground, like that. Okay, so we're just going in, across, 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 and then this is the easy part, the part that you don't have to worry about blowing out any fuses. There is a part where you have to worry about blowing out fuses, but this isn't that part. So then you just go across here, you go across here, and then you can go across here. Like this. That's your total. This is across 1. This is across 2. And you don't even care whether you got a positive or negative, because if a measure's negative, it just means you guessed wrong. With an analog meter, you do have to be aware of that. But here, you don't have to. Okay, now, what we should find, as the electrons go through each resistor, they're dropping in voltage. How do we know that? Well, we know that because this side is, let's say, 10, and this side is 0. So that means that some of the voltage has to drop across the first resistor, and some of the voltage has to drop across the second resistor. Why? Because there's a potential energy change, and Q delta V is the value for that potential energy. Okay? And so this is proportional to the amount of work that's done on the charge. But you can think of it just in terms of the potential alone. And so if you had a waterfall with 2 drop-offs like that, you'd have a drop in gravitational potential energy there, you'd have a drop in gravitational potential energy there, and then you'd be down at the ground level. And so this total height here, h, would be equal to h2 plus h1. Say that h equals h2 plus h1 plus h2. Similarly, if we stretch the circuit out, and that's sometimes what I like to do so that we can use our gravity analogy on it, I'll make this the plus 10, then I'll make this resistor R1, and this resistor R2. Then we can think of this drop in voltage as being like our H1, that's our V1. And then this drop in voltage there is like our V2. That's like the drop to this height. And then down here, this is zero potential, and so we sometimes write that as ground. And then if you stretch your circuit out like this, then the ground side is just this side, and the hot side is that side, where I got the dot. And so then the total is just V1 plus V2. And so that's what we get in a series circuit. V total equals V1 plus V2. And if we had 3 resistors, it would be V1 plus V2 plus V3, which we'll get later. So now we use Ohm's law. Ohm's law is kind of like, and I'll derive Ohm's law for you later, but it's kind of like F equals ma. It's our most basic equation for circuits, even though you can be broken down to more elementary things. It's the easiest way to describe everything. So I can write V total as I total, that's the total current flowing through the circuit, times R total, equals I1 R1 plus I2 R2. And from that, I can also make the conclusion that I can come to the conclusion that because there's nowhere for the electrons to go other than to flow right through the wire, the current has to be the same all the way through. And so in other words, I total can't be any different than I1 or I2. They've all got to be the same because there's no other place for the charge to go. There's no forking. Now when we get to parallel circuits, which we're not going to do today, we get to parallel circuits, then you can have different ways. It's like a stream branching off, going in different directions. But if you just have a single stream, and then it goes over a waterfall, and then it comes along, and then it goes over a smaller waterfall or something, the amount of water flow anywhere has to be the same in gallons per second or whatever, because the amount of water in has to equal the amount of water out. Similarly here, the amount of charge in has to equal the amount of charge out. So therefore, these are all equal and can cancel out. And so that gives us a simple relationship for the total resistance. R total is just equal to R1 plus R2. If you had 3 resistors, it would be plus R3. Okay, and so those are the main relationships. Then we could find, if we wanted to, we could say that I total is equal to V total divided by R total. But once we have the total current, so what does that mean? Well, here before it gets to any resistance, we call that I total. Here across resistor 1, we could call that I1. Across resistor 2, we could call that I2. And when it is gone and it's coming back into the battery, we could call it I total again. But clearly, there's nowhere else for the charge to flow. So I total is the same. So that's the beauty of a series circuit. Once you've calculated I total, you know it all the way through the circuit. And that's not the case with a parallel circuit. And so this is the simplest case. And so this would be your delta V, either 5 or 10 volts. I'll just do the 10 volts here. Divided by R1 plus R2. That would be 500 ohms plus 1,000 ohms. Okay, so that would be 10 divided by 1,500, or 1 over 150 amps. And so this will be displayed then as a small fraction of an amp. Okay, and that's good, because a half an amp will kill you. And so we have low voltages and high resistances in these labs so that we don't kill you. And, but when you get to 2.8C, it's a different story. You know, there's some real dangerous stuff going on there, but we don't need to concern ourselves with that right now. Okay, so what I'd like you to do then is to measure the current too. So you measure the voltage. I'm going to want you to measure the current. So here's the set of steps. Here, you put first two resistors in series, measure V1, V2, V total, and show that the total voltage is the sum of the two. Then measure I, which is I total, that's V total over R total, and do a percent difference between the value of R total that you calculate and V total that you calculate and the value that you measure. And so here's the trickier part of the lab, not really that bad, but a little trickier, is that you need to measure the current. So to measure the current, what we've got to do here then is to, first of all, we need to change the plug configuration. So we're gonna leave this in common, but then we'll move the red one over to the middle, like that. So you got to start with that. And so once you've got that, now you've got this thing set up as a completely different circuit inside of here. And I'll describe to you later how these things work on the inside to make that happen. But you don't want to go all the way across like this unless you're measuring amperes. We're measuring milliamps, so it's going to be more accurate, way more accurate, to go with these two in the middle. Then you don't want, here's the thing that, no matter how many times I say this, there are some people that still just knee-jerk reaction is to do the wrong thing. And this will blow the circuit. And if we blow the circuit, it's not a huge deal, but it's going to put Mark to work replacing fuses when we would rather have Mark out here helping us, right? And so we've got our circuit set up like this, but what we need to do in order to measure the current is to get this thing right in the flow. Okay, and so we've got positive and negative, so it's set up like this. So we'll have the hot side come out like this, and that can connect in to the hot side of our current meter, like that. Okay, so this is just, instead of going straight to the resistor, it's going to the hot side of the current meter. And then the negative side is going to go to this point over here on the circuit, where we had the wire directly hooked up before. So essentially what we're doing here is we're putting this resistor into series with these two. Okay, and so this is the difference between what we call a series measurement or a parallel measurement. So by doing it this way, then the meter is going to look something like this. Here's your battery, and here's your meter, and here's your resistor R1, here's the current meter. And here's your resistor R2, then back around to ground like that. So that's how you measure current. You measure it this way, with the two things in the middle, that's when you put Mark to work. Because then, the current meter needs to have low resistance. Otherwise, it's going to add a resistance to this thing, and it's going to affect the very current it's trying to measure. And so we want this to be low resistance so that our total is just R1 plus R2 plus some little tiny number, which is the resistance of